Yeah, okay. I was also going with the fact that it is being pulled or pushed in the direction of the electric field, so it has to be positively charged. But reading also helps. And I paused it again, there we go. 1 microcoulomb. So F Q is 1 microcoulomb. All right. Well, then given the mass, I can find the weight. How do we do that? Okay. What is G there?
Is it gravitational force?
No, that's weight, it would be the gravitational force. What is little g?
9.8.
Pardon?
9.8.
Do you want to give me some units on that?
9.8 meters per second squared.
Yes, and what is it?
Acceleration due to gravity.
There we go, down to get the acceleration. So we got, as a group, we got it. We are assuming, if you're saying it's 9.8 meters per second squared, what assumption did you just make? Okay. So my weight is going to be equal to mg, which is 0.005 times 9.8 meters per second squared, and that is 0.049.
Yeah.
All right, so I have the force down. Tension can't quite find yet. The electric force. What formula should we use for electric force? Right now, an additional noise of the computer is fighting you.
Is it 1 times 10 to the negative 6?
That would be the charge. What formula do we use for the electric force?
1.6 times 10 to the negative 19. Or no.
All right, say it again.
1.6 times 10 to the negative 19.
No. Formula. We actually have 2 formulas for electric force.
I use Q times electric field.
Yeah, that's one of them. So the other formula, if I have 2 point charges, I would use KQ1, Q2, this is the electric force. I guess the magnitude of the electric force over R squared. So if I'm given 2 point charges, I can use this, but I'm not given 2 point charges. I'm given a uniform electric field and I'm given the charge. And so the other formula, if I'm given that information, the magnitude would just be QE. Actually, I really don't need those. If Q is positive, then the electric force and the electric field are in the same direction. If it's negative, then they're in opposite directions. So this is going to be QE. All right, so we did the force diagram. There's no acceleration. Coordinate axes. And for those who have forgotten, I'm taking you through the facades method. Force diagram, direction of acceleration, come up with your coordinate axes, you decompose, break up any vectors you need to, come up with the equations of motion, any substitution, then solve. So, how should we set up our coordinate system?
I guess right, positive.
Okay, so you want to go right, positive, and, okay. Now, if you chose up or down to be positive or left or right to be positive, that's between you and your God. However, why is this coordinate system, vertical, horizontal, the best one to probably choose? Because there's no acceleration, there's a lot of choices we have here.
Because it lines up with two of our forces already.
So now we have to only break up one. All right, so we have our coordinate system there. Break it up. What are we breaking up now?
Tension.
Yeah, that's the only one that's not horizontal or vertical. And so I've got weight acting down. I've got my electric force acting to the right, up. It is the adjacent side, so this would be Ft cosine of 8 degrees, and therefore this would be Ft sine of 8 degrees. I know that's the angle that's 8 degrees because if I think about it, I have two parallel lines here cut by a transverse. Alternate interior angles are congruent for those with that geometry. So now, what are my equations of motion? Equations of motion. This bring back all sorts of fond memories, I'm sure.
Too bad my memory is terrible.
Yeah, oh well. When I say equations of motion, what is the, I guess, template equation? What am I plugging into?
Force equals mass times acceleration.
That's the one. So I'm plugging in F equals ma. I'm gonna have two equations because I have one object in two directions. So give me one of the equations.
T cosine 8 degrees equals weight.
Equals what?
Weight.
Yeah, I'm gonna go ahead and put in the intermediate step. Minus the weight is equal to 0. You're absolutely right. That's gonna eventually translate into Ft cosine of 8 degrees is equal to mg, or 0.049. All right, and the other one?
Ft sine 8 degrees.
Was there more that was said and I just missed it?
No.
Someone else wanna fill
It
in?
should be negative.
Given the Erica convention. Still, it's not an equation yet. This would be considered a term.
Plus.
Pardon, plus? We're dealing with horizontal forces here. I have only two. We've identified one of them,
Plus QE or FE.
Fe. There we go. Now we have an expression.
Equals. Wait. QE.
Pardon?
QE equals Q.
Oh. I'm putting the intermediate step in. Again, you get to a certain comfort level, you can just jump ahead, and that's fine. I have no problem with that. But let's go ahead and finish this.
0.
Yeah. It's the mass times the acceleration. Well, I know the mass and I know the acceleration. Acceleration is 0. All right, so that would then go into, we have Q E equals Ft sine 8 degrees. I know Q, I know M, I know G. I have two equations, two unknowns. It's a matter of solving. However you want to do it. Let's do it the math fun way. So I have Ft sine of 8 degrees divided by Ft of cosine of 8 degrees. It's going to be equal to QE over mg. So I just did that divided by this is equal to that divided by that. Denominators are equal, numerators are equal. Ft goes away, we have to get rid of it somehow. And solve for E. E is equal to mg tan of 8 degrees divided by q. And yes, I did change my q halfway through the problem from a big Q to a little q. Let's make it official. And now it's plug and chug. So mg is 0.049, tangent of 8 degrees divided by, that was 1 times 10 to the negative 6th. Over there somewhere, I think. Yes, there it is. So you plug into a calculator, you get an answer. What are the units? It's gonna be somewhere around, oh, no, it's gonna be smaller than I was thinking. Anyway, what will the units be? Joules? If you're stopping there, no. Not the simplest way of going about it if you want to start with joules though. Units for electric field.
Newtons per column. Newtons per column.
Coulomb.
Coulomb.
Yeah. So I'm gonna get something newtons per coulomb.
6.88 times 10 to the negative 9.
You got something different?
Yeah, I got negative 3.33 times 10 to the
If you got a negative answer, then I'm guessing you're in radians and not degrees.
Yes, I am.
Okay. Other questions?
I know it's going backwards, but can you just tell me, how'd you get 8 degrees?
It was given in the problem.
How does, oh, in the book.
Yeah. Yeah. In the picture, actually. Yeah, it's in the picture itself. Presumably in the solutions I didn't provide the picture.
In the picture, it just shows a beta sign. Well, in is the packet.
Yes, Stephanie and or Ryan.
So I'm a little, how did you get QE over MG?
How to get QE over MG?
Yeah.
I know, are you good with those being equal and with those being equal?
I still don't completely get the QE.
Louder, please.
I still don't really get the QE part.
Right, but are you good with
Yes.
this equation? Are you good with this equation?
Yeah.
Okay, so what I did is I took this equation right here, that they're equal to each other. And the math people insist if I divide both sides by equal things, it's okay, as long as it's not 0. So I divided QE by MG, and I divided FT sine 8 degrees by something equal to MG, which was this.
Oh, okay.
So that's what I did there. So that would cancel the tensions out. The reason I did it is cancel the tensions out. Alternatively, you could have solved for tension, actually come up with a number plugged into there, solve for E. Is that sufficient?
I think so.
Not 100%. I've done this type of maneuver before when we were dealing with banked roads. That's probably the most common place where I do this technique where I All right, well, Stephanie, you had a question. Is it a different problem? All right. Ryan, did you want to do, let me write that out slightly differently. if I have x equals y and a equals b, then if I start out with x equals y and then divide by a, that's legitimate math, as long as a is not 0. A is also equal to b based upon that equation, so instead of an a there, I could just write a b.
Oh, okay,
That's what I did.
okay.
All right. Stephanie?
I found that question.
Okay.
It's number 41.
What is the force on the charge located at 8 centimeters? Given Q is 1 microcoulomb. All right, so A, figure A,
I understand the math. I'm just not sure how you knew which force was negative.
what do you mean which force is negative?
Because in this equation it has the force of the one at 5 meters.
Force of the one at 5, oh, you're on part B? Okay,
Being subtracted from the force at 3 meters. Not being subtracted from.
all right. Louder, please.
In your equation, you had the force at 5 meters positive, and then the force at 3 centimeters away negative.
Right.
How did you know which one to put as negative when they're both positive charges?
All right. Sync up. It could be all right, so 41, force on the charge at a location of 8 centimeters, given that Q. It tells you right there, positive, negative, positive.
How did you know to subtract this one from that one?
Oh,
Sorry, I couldn't really word it.
okay. In that particular case, if you plugged into this right here, let's actually write out. The force on 1 from 2, case of E or C, Q1, Q2 over R squared, R2 hat. All right, so the force on that middle charge, based upon the left charge, is going to be so if we have A, B, and C in line, the force on B from A is going to be, well, they're opposite signs. It's going to be some negative number, R A hat, which means it's being attracted to A. The force on there we go. The force on B from C is going to be, again, some negative number because they're opposite charges, R C hat. R, at this point right here, R A hat is going that way, the unit vector. At this point right here, R C hat is going the opposite direction. So they are opposite. So if I put them in terms of a common reference frame, they are opposite signs. R C hat at this point is the negative of R A hat. So when I add them together, so it's going to be negative some number, I'll just put X, R A hat plus negative some number, R C hat. That would be the total because I'm adding them together. And then to get these in terms of the same reference, probably the simplest is, why don't I just make to the right positive? So R A hat is, so this becomes negative X, R hat, negative X plus negative X. Well, that's negative direction, so negative.
Okay. So if I were to make, like, to the right negative, the opposite would be true?
Yes.
Okay. The only other one I had questions on was number And
electric field at the location of QA?
Yeah. And I think it was more your explanation that was confusing.
Alright, so find the electric field location of QA in figure 18.54, given QB, QC, blah, blah, blah. Alright, and what was the, is there a specific question you said?
Part A.
Part A. Alright, so first off, QA does not exert an electric field on itself, as was discussed yesterday for some of you. So it's the electric field from B and from C. So I've got a -5 microcoulomb charge down here, and that's QC. And then QB, I have a 10 microcoulomb charge, positive. What is the electric field at a point up here? Equilateral triangle? Yes. And distance between them, 25 centimeters aside. So the distance between here, 0.25 meters, 0.25 meters, 0.25 meters. And that distance is given in the figure caption. Well, first off, I know the electric field goes towards negative, so if I'm trying to figure out here, it's going in that direction. So this would be the electric field at point A because of C. And here, it's positive, so my electric field's going away, so this would be my electric field at A from B. So I just need to figure out the magnitudes and then add them like vectors. Is that, keep going? The magnitude is going to be 9 times 10 to the 9th times 5 micro